Everybody. My name is Jay. I'm from Northeastern University. So in the previous video, we talked about this problem that we're trying to solve, which you will have to watch the previous video to understand. Basically, an optimization with an orthogonality constraint. And in the last video, I think we figured out how to find the Lagrangian and set it to 0, which was we used as an optimal condition. We did not look into the second order condition, mostly because I don't think it would really contribute that much to your understanding. But if you're interested, definitely read it. Well, so now that we have these optimality constraints, I want to move on to actually how to find the solution of X. Now, just as a reminder, the problem is f of x. We're trying to minimize some function subjected to the constraint that x transpose x must equal to identity. So that's the problem we're trying to solve. So let's look at a very simple example. With this is a very simple example because f of x is essentially equal to 0, right? 0, 0 here. That's 0. But I wanted to subject it to a orthogonality constraint. Now we know the solution of this is like basically a flat plane on 0, right? It's just a plane. But not because of this constraint, and now it can't be anywhere on the plane. It has to be on the circle. And this is one way to look at it. Basically, any point on a circle is a possible solution. Another way to look at this is more in a 3D case. Like we look at it in a 3D, imagine a cylinder, and the point of intersection between the cylinder and the plane is essentially the possible solutions. Now, a standard approach to use some kind of gradient descent and keep going downward while satisfying the constraint. But we can actually look at another way. Think of this cylinder as kind of like a burrito that you can unwrap. Yes, the burrito that you would eat. Like a round cylinder, like a burrito, and you unwrap it. And over here is the point of intersection, like you see here. Like I want you to change your perspective from this perspective and see it from the perspective of the cylinder. And when you unwrap the cylinder, the point of intersection is this line. Now, why do I want you to see it this way? Well, let's look at another example. Instead of 0, 0, now it's 1, 0. Okay? Which means that in one dimension, the x dimension, it's actually tilted. So as you can see, the plane is now tilted. Now let's try to do this same perspective shift. When we do this perspective shift, the point of intersection from the perspective of the cylinder looks like a simple curve. Well, this is very interesting because if we can solve this problem on a simple curve using something like gradient descent, it is very easy to do. Whereas from this perspective, it's very difficult to do. Now, based on this paper, that I think I listed in the comments what the paper is. Everything we are doing here is actually based on this paper. Not only can we optimize on this space, there's actually a method very similar to gradient descent that we can apply. Now, if you remember gradient descent, well, you have some x, and you can update to xk plus 1. So you will go from k to k plus 1. So you get the next x. When you do an update by subtracting the step length and the gradient. Now, when we are optimizing on this manifold, notice how everything is the same except this part here. This part here. Now, you may remember from previous lecture that AX is actually the gradient at the point of at the optimum point. So this kind of makes sense. It's similar to like a derivative of a function, in that this is similar to a derivative of a function. I think it would require another lecture separately just to explain the geometry of this. But for now, just treat it like it's similar to gradient descent, and this is, you can think of this as the gradient, like very similar to the gradient. So the two equations look very similar. Now, we can just stop here, and you can literally just use this function until it converges. But I think what would be helpful is to prove that with this equation that we're optimizing on the manifold. We're actually doing the optimization. Well, to prove this, we need to demonstrate two properties. The first property is that as you update from k to k plus 1, you go from one x to another, the new location still has the Stiefel manifold constraint. So notice k plus 1, when you multiply them together, it's still identity. So no matter how you update, you're always on this cylinder. And the second thing we want to show is that as you update, the new location, the new cos function, previous one. So not only are you staying on the cylinder, you're actually going lower, 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 and lower. So yeah, this is a very, if these two conditions are met, it essentially says that what we were doing, like this part, right? Optimizing from this perspective. That's what's happening with where is that equation? Yeah, with this equation. So let's prove these two. We'll start with the first proof. The first proof says by using this update, this thing here, the new xk plus 1 is still on the Stiefel manifold. So we start with this equation, and I'm going to multiply here, and I'm going to multiply here. And then I notice here's k plus 1, k plus 1. So I'm going to move this over here. So once I move this over here, I notice there's k, k, right? So I can organize the two k's here, and k plus 1, k plus 1. I can organize them here. And lastly, I'm going to move this thing over here. And when I move it over here, we now have a clean relationship from k to k plus 1. Of course, we can call this matrix something smaller, like cube, for example. But sure. Therefore, when we multiply them together, we can use the larger expression and get something like this. Now, we know that this times this was identity. And we'll call what's inside it like a phi. Therefore, if phi is also equal to identity, then xk plus 1 is also equal to identity, because essentially you're getting rid of this. And we know that this is identity. So we don't need to prove this whole thing is equal to identity. We can get rid of this and just prove that the middle is identity. So I want to show, you see, the middle is the identity. I actually think this is a plus. I think that's a plus. Okay. So to prove this, we need to first realize two interesting properties. The first is that the Cayley transform matrix A, the transpose of that is actually equal to the minus. And this is, you can prove it in 2 lines. Just write it out, put a transpose, and you see that it's the negative. And the second property that's interesting is if you have a matrix B, identity plus B times identity minus B, you can actually flip the sign. Right? So notice here's plus minus, here's minus plus. And that's also very easy to prove. You literally just multiply it out. So with these two properties, we can then start the process. So over here, the first thing I'm going to do is look at these two terms and then combine the identity to the inverse together. When you do an inverse, they actually rotate spaces. So notice the t is here and the t is here. So like I told you before, A transpose is equal to minus A. And therefore, given this transpose, I'm going to convert this into a minus. Convert this to a plus. You see that? And then notice this is a plus, identity plus some matrix, identity minus some matrix. It implies that we can flip them. So I'm going to flip them here and flip them here. And now I'm going to redistribute the inverse back in them, which flips them again. You can see that when you multiply this, you multiply by its inverse, right? This times its own inverse, which is identity. This times its own inverse, which is identity. Of course, identity times identity is identity. And we have proved it. Essentially, we've shown that this right here is an identity. Therefore, k plus 1, xk plus 1 transpose times xk plus 1 must also equal to identity. So we have proved the first requirement, which says that every time we do an update, we're staying on the manifold. We're staying on the cylinder. You remember that cylinder? So now we're ready to do the second proof. We're saying that when we do an update from k to k plus 1, we want the new location to be less than the previous one. So it's going downward. We have shown previously this relationship, right? Essentially, that turns into some Q matrix. This equation tells us that xk plus 1 is a function of alpha. Obviously, xk plus 1, alpha is here. And where, if I must remind you, alpha is the step length. We also know that xk plus 1, f of xk plus is a function of xk plus 1, obviously. And therefore, this function can also be written as f of k plus 1 alpha. Now, if the gradient of the f at k plus 1 in the direction of the step length is negative, then there exists a small enough alpha such that this is true. So you can picture, we want to show that the gradient at the current point, right, at the point where alpha is 0, so the point you're about to go down, if we can show the derivative is equal to negative, then it basically tells us the function is going downward. It's getting less and less. Or we can write it this way more officially. The gradient of the function with respect to alpha at the point where alpha is 0, if that is less than 0, then we have proved that, well, we have shown that the direction is downward. So let's take the derivative of this with respect to alpha. We can use the chain rule. So the chain rule says that, okay, we want to take the gradient of this with respect to x, and then we take the derivative of x with respect to alpha. Now we know how to solve this. That was just g, the gradient, also known as this here. So all we really have to find is this here. So over here, I'm going to write this in a simpler form. So this is literally the same thing of this. It's just written in a more in a compact form. And this right here is equal to this. So like I said, this right here is just g. And this right here is what we need to find. Now, if we can find both these two terms, multiply them together, and if they're less than 0, this means that the direction is going down. Down. Okay, so how do we solve this? Well, we know this equation here. That was the update equation. So the first thing I'm going to do is I'm going to distribute them here and here. And then I'm going to take the derivative of this with respect to alpha. So this right here doesn't have alpha, so it goes away. Over here, we get rid of the alpha, so that goes here. And over here, we just use the chain rule. We take derivative with respect to alpha and gets this, which is here. And then we take the derivative of this and then multiply by this. So here's the derivative, multiply by alpha a. Now, we're going to combine the terms. Here's k plus 1 derivative, k plus 1. So I'm going to move this over here. And notice minus a, minus a. So I'm going to pull them out. I'm going to pull this one out. So here's k plus 1, right? So k plus 1. I'm going to pull both of them out. And lastly, I'm going to move this back here. So this will become an inverse. That should be a plus. Of course, if you now set alpha equal to 0, this cancels out. And this just equals to 0, which we got right here. That was quite a bit of math. Now, if we have xk, right, and with some step length, we go to xk plus 1. Now, if alpha is equal to 0, it means this distance is equal to 0, implying that xk is actually equal to xk plus 1. That's how I got the 2, xk. Okay, now we know what A was. A was equal to what? Gx transpose minus xg transpose. This is the Cayley transform, and I'm going to plug this A right here. So now it's minus 2, and then here's A. Okay, now that we know this term, right? Remember, we were trying to calculate the gradient. So we found this term. We're going to plug it in now. This is equal to g, and this part is equal to this part. The minus 2 is here. Okay. And first thing I'm going to do is move this over here. So with trace, you can rotate them, and it still equals the same thing. So that's over here. Once that's done, I'm going to multiply here and multiply here. Okay, that's how we got this here. And I'm going to do something interesting. We have a trace term, right? Trace of, let's say, some m. I'm going to do this. Trace plus trace of m divided by 2, which is the same as trace of m. But it's a math trick that I'm going to do. So you see, trace plus itself. Now the 2 is going to cancel out. Once the 2 cancels out, I'm going to combine the 2 traces together. Like, I don't know if you know this, but trace of A plus trace of B is equal to trace of A plus B. So I'm going to combine what's inside here to get you this much larger term, which we then can convert to this form here. Basically, they're the same thing. If you multiply them out, they're the same thing. And what do you know? This right here is A. This is A. This is A. So we have A transpose A times trace. Oh, this right here is essentially also known as the Frobenius norm. This right here is the Frobenius norm, which is known to be always positive. Which means that if this is always, well, positive or 0, if this is always positive 0 multiplied by a negative, voila, this term must always be a negative, well, it will never be positive. Let's say that. It will be 0 or negative. So if you remember the 2 properties, the first, we show that as you do an update, you go to a new location, the new location still satisfies the Stiefel manifold. In the second one, we show that as you do an update, every time you're going lower, lower, and lower, so it behaves very similar to gradient descent, while simultaneously staying on the manifold. In conclusion, we can solve a problem with a Stiefel manifold constraint with a scheme very similar to gradient descent, right? That's something like this. Now, of course, we want to simplify this with the other equation. So here's the other equation, where you just multiply the current location by this matrix here. And once you do this update, you have found xk plus 1. Of course, then you can do it again. Xk plus 2 equals to q xk plus 1. And you can repeat this process until basically xk plus n equals to xk plus n plus 1. When they're approximately equal, then you can just stop. So I think that is it. Useful. I don't know how many people will need to do orthogonality constraints in the future, but I just learned it and I think it's pretty cool. Anyways, thank you very much. I will see you later.